Thank you for coming, and I'm just very excited to be here. And because this is a very interesting topic, and I want to share with you words as vectors. And this is also, co-sponsored by the UIS AI Campus Learning Community. And so let me just get it started. Oops, let me start this. Oh, yep. Hey, before I talk about the math here, the future is here. This semester, I'm also teaching a class on quantum computing, and we are exploring different quantum computing programming language. Now, a lot of major companies like Google, IBM, Microsoft, they all have their own, quantum computing programming language. Now, some of them actually have quantum computers, but for Microsoft, the upshot is that, well, they also have a quantum computing programming language, this Python based, and they also have a web page so you can learn their quantum computing programming language called Q#. This is what the page. If you go to that page, it says learn with Azure Quantum Catalyst. You will find that just like when you go to a lot of websites, you have a chatbot on the right. But this, what I want to point out is we are looking at the future of education. This, the Microsoft, this page to help you to self-paced tutorial to learn their quantum computing language. It comes with a chatbot. Come with a chatbot so they can help you with how to learn, the programming, their quantum programming language. Most people think maybe experience that you can use chatbot to have business related, or maybe is for individuals, planning a trip to somewhere. But in fact, in education, you are seeing this is give us a glimpse of what education will be like in future. That all these online resources will come with a very smart AI chatbot to learn technical stuff like programming language and stuff like that. And in fact, because I know this is from Microsoft, so this chatbot is powered by OpenAI GPT-4. So Anyway, I asked it a question unrelated to quantum computing to test, how good it is. And actually, I asked it to help me to plan a day trip to Chicago. It works out. It works out. But when I asked it to give me some Python, programming tips on machine learning, it refused to answer me. Hey, but before we go on to the technical stuff, the math stuff. Before we go on to the technical stuff, let's get some names correct first. Oftentimes we heard about ChatGPT from OpenAI, Bard from Google's. Now these names were actually refer to these are AI chatbots. These are AI chatbots. Well, technically, it's more than just chatbot. That's the apps that we human we use it, we interact with. Now, but the brain, the engine behind all this app, behind all these AI chatbots are what we call language models, LM. Yeah. Now, language models.
Listen, guys, can you be quiet, please? Can you get your folders, please?
I'm going through a pen at Gina. Now Gina threw it back and hit it. We should do no work the way you right.
Looks like we have a lot of audience. Thank you, Monica. The brain or the engine behind all these chatbots, for example, is these these models. Now, language models are in fact statistical models that are designed to handle natural language processing tasks. And they are designed with a lot of statistical theory, statistical model behind. And the name GPT, despite the fact that you see in ChatGPT, the engine or the brain behind ChatGPT is also called GPT. It actually stands for Generative Pre-trained Transformer. So these are the names, and for the Google's one, they have Plum, they have Lambda. But one thing that you want to, we will be talking about quite a bit is the word is transformer, and it will play a big part in today's talk. Now, these models are trained with extensively with a lot of data. They train with hundreds of billions or even a trillion of words. They are trained with a lot of data. Now, when you have a AI model or machine learning model that are being used, that you need to train with such a massive amount of data, that means a lot of money. That's why the $3 signs there. In fact, all these language models where they have to train multiple times. Every time when they train, it will take days. And every training sections, the estimated cost is in terms of millions of dollars. And this is because of the massive data we use to train this model. That's why we call it large. These are called large language model. And other reason we call it large language model is because the number of parameters involved in this model is just enormous. Roughly speaking, the number of parameters, the more parameters you have in a model, in general, give the model better capabilities to handle what it's supposed to do. And so you see in the GPT families, the GPT-3 and 5, it has like 175 billion parameters. GPT-4 is estimated to have over a trillion parameters. So it's just huge. That's why we call these language model large language model, trained with a lot of data, and they have a lot of parameters. Now, getting all those names right for today's talk, I want to pinpoint some big ideas behind the recent breakthroughs in large language models, and in particular, I want to talk about some of the math concepts that play a key role in these particular developments. And these math concepts are not something super difficult. They are, in fact, some of the math that you have already learned in linear algebra. Now, words as vectors. Why did I choose this name? It's because simply computer can understand only numbers. So in order to help computers or to make computer to process languages, words, we have to somehow, the first thing is to code words into numbers, in particular vectors. Now this encoding, we have a name for it, is called the word embedding. So the goal of word embedding is to code words into vectors, and hopefully these vector representation of words will have some being meaningful, will capture some meaning of the words and relationship of words. Now, in fact, language model, natural language processing has been, computer scientists and other scientists have been studying this for quite some time. But just that in recent years, just in these 2 years, because of ChatGPT, things really took off. And in fact, before all these recent developments, back in 2013, from a team of Google scientists, they actually create a pretty interesting, quite powerful word embedding algorithms. Their algorithms, actually, there are 2 of them, but I would just, talk about just one before we go on to the transformers and stuff like that. But because this will set the stage of, how words can be understood as vectors, and it will also help, help us to understand the rest of the talk. And I just want to focus on just one of the algorithms called the continuous bag of words, SIBO. Now, and the goal of SIBO is to predict a target word based on its context. So basically, if you give this model some a sentence and one of the word is missing, so it's just supposed to be in high accuracy predict the missing word. And in fact, they did a very good job in these algorithms. They actually could create, they can code and embed words into vectors of dimension about 500, meaning these vectors have a three-dimension vector has 3 components. And here we are talking about 500 dimension vectors. And so each of these vectors would have 500 components. And the good thing is that this vector is able to capture some meanings of words in the following sense. Now, this is one of the most famous example of what, these algorithms can do. Oh, by the way, the SIBO is one of the algorithms, but we usually refer that algorithms as word-to-vec on your left-hand corner. As the name suggests, it is a algorithms to map a word to vectors, and SIBO is one of those algorithms. This is a very famous example of what SIBO can achieve. Now, turns out they're able to do the following. After they successfully trained their algorithms, they found the following phenomenon. You take the vector that they create for the word king, subtract the vector representing men, the word men, plus the vectors representing woman. So because you can add and subtract vectors just like you learned in Cal 3 or in linear algebra, turns out they found that the vector for king subtracting the vector for man plus the vector of woman is approximately the vector represent queen. So it just, you see that, their algorithms do capture in certain degree the meaning behind this word. And how did they do it? Now, this is where the math part comes in. Now, suppose I give you a sentence: pizza and Coke go so well together. So in particular, the word Coke has 2 sets of context words. One is the 2 is before them, 2 is after them. So their SIBO is trained in such a way that if you take the vector that they found for the word code, it should be approximately equal to the average of the sum of the vectors representing the context of the word cook. What it means is in this particular case, if you don't go to the word cook in this sentence, you go to the left neighbors, the 2 words from the left neighbor, pizza and you take the 2 vectors representing, one representing pizza, plus the vector representing the word and plus the vector representing go, the other the context word on the other side, plus the vector representing the word so. You add them up together, you take an average divided by 4, and that will be approximately the vector representing cook. This is the criteria for them to design their algorithms. Now, of course, this may not be how we humans understand, words in terms of its context, but this is what they did. And they seemingly found a pretty interesting algorithms. Now, of course, SIBO is pretty interesting, but it neglects, word orders or even grammatical rules. So if we want to have algorithms or models that can really generate a conversation that can really get a deeper grasp of, human or languages in general. We need something, better than that. And it happened around 2017. A major breakthrough is in this paper. Attention is all you need. The authors here are from Google. In this paper, they propose this transformer architecture for language models. Now, this paper was published in 2017, and it has been cited over 100,000 times. It's a lot of citation because the transformer architecture it proposed, it becomes the standard for language models after that. All the major large language models we are having today, the GPT family, the Plum and Lambda, the two that Google is using, they all are transformer-based model. And you heard me right. Yes, even the one from OpenAI, they are also transformer-based language models. And this is the main thing for today's lecture. I want to, give you a highly simplified version to show you how the transformer architecture works in the context of language models. And so for illustration purpose, I will be just highlighting, just a few, important features and ignore a lot of technical details. And for the details, I will have some reference post at the end, so you can you can go back to and look at that. But I'm going to give you a very simplified version of it to give you a sense of how it works, and in particular, some of the math that you already have learned in your classes. Well, they are the foundation of the transformer model. So suppose I give you a sentence. Well, I give it a sentence, give the language model a sentence, and ask it to guess to generate the most likely the next word. Okay, it's pizza again. So that sentence is, I like pizza and blank. So suppose that, we're able to encode these 4 words into 4 corresponding vectors, x1, x2, x3, and x4. Now, in reality, if we are to encode these words into vectors, they will have, these vectors will be having dimension of 500 to 1,000, okay? It's not just 4 blocks or 4 components. No, just for picture, that you see 4 components. In general, they're much bigger. So imagine that I'm able to encode, them as vectors. And what does transformer do to these 4 vectors that can make, language model so smart? Just like that, the title of that paper suggests, attention is all you need. It's the attention mechanism that help these words, each of these words, to capture some degree of understanding of context of the input sentence. And in this particular case, we also call it self-attention because it's in the same sentence, same input sentence. This self-attention or attention is to help each word to understand how it should be related to other words, how much emphasis it should be paid to different words in the input sentence. So for example, the word like, how much it should emphasize, how much attention it should give to all other words. Now, what it does, what attention mechanism does is in fact linear transformation, and something that you learn in your linear algebra class. Now, take for example the second vector. Now remember the original sentence, I like pizza, and so the second word is like. After it is being embedded as a vector, it's represented by x2. that vector x2, what does attention mechanism, what does it do to it? It transforms it to another vector called h2. h2 turns out it's simply a linear combination of all the vectors in the sentence, x1, x1, x2, x3, and x4, as I show you on top of the page. And so turns out, this is basically the one of the most important trick that makes language model works, is this linear transformation called attention mechanism. Now those A's, A's21, A's22, A's23, A24, they are, coefficient, and that's the trick also. That's a trick here. For example, the coefficient A23, why the subscript 23? Because we are talking, this is because it wants to capture how much the third word affecting the second word. Now, because the second word is the target word that it's being transformed from H, so it's being transformed. So the vector is transforming from x2 to h2. And so that's why the subscript is 2, 3. Now, but how should we choose that, a coefficient? This is the insight of that paper. Now, this is a highly simplified version. The main idea is that particular coefficient capturing how the third word influencing the second word is proportional to e raised to the power to the dot product of x2 and x3, x2 and x3, the dot product of these two vectors. That's the one of the main insights. Now they can actually assume a different kind of formula here, but they choose this one. There's some history behind this, but I want to point out that it's the dot product that you learn in Cal 3, the dot product that you learn in linear algebra. That is where it goes. So roughly speaking, if that two vectors, x2 and x3, if in that vector space, these two vectors representing two words, if they are kind of related to each other, so in a sense, they might be pointing in a similar direction. In that case, their dot product will be large. Now, if they are not that related, so we will have a scenario that these two vectors are kind of perpendicular to each other. Then the dot product will be small. And so the weight, the coefficient A23 will be smaller, meaning the third word will have much less influence on the second one. Now, let me remind you what is a dot product. Now, you learn, in Cal 3 or in linear algebra, maybe dot product of three-dimensional vectors. For high-dimensional vector, it's the same. Suppose you're in a k dimension. These vectors are k dimensions, so each of them has k components. So the dot product of two vectors is simply you go to take the first components, you multiply them. Then you add the product of the second components from the two vectors. You keep adding all the product of corresponding components until you cover all n of them, sum it up together. That's the dot product. And this is where it goes into that coefficient. That's the basic assumption of the model. It turns out it works pretty well. It works very well, this assumption. Now, after this attention mechanism transform the x vector to the h vector through self-attention layer there. So we have 4 vectors, x1, x2, x3, x4 in the middle. Then we pass these vectors into a small neural network. Now, this is no place to talk about neural networks today because it's just, we don't have time. But all that you have to know for today's talk is that these machine learning models inspired by biological neurons. And for today's talk, you need to know that these are basically nonlinear functions. That means they will take the inputs. Maybe they will have they will then mix them up in a nonlinear ways, and to create some outputs. It turns out from our experience with neural network, these nonlinear features, this nonlinearity, will usually help the models to have some more complexity, will add some more complexity to the model itself, which in turn allow these machine learning models to have better ability to understand more complicated pattern of the data. But for this, as far as the transformer architecture is concerned, the neural network is simply function as some sort of post processing, for these signals H1, H2, H3, and H4. And after they process these H vector, they give the final output Y1, Y2, Y3, Y4, corresponding to the original 4 words. But now they have been transformed by the attention mechanism, and also mixed it up by the by a neural network. So we call this these processes a transformer block, Now, theoretically speaking, once you get Y1, Y2, Y3, and Y4, we have 4 of them because the input sentence has only 4 words. You can simply take the last word, Y4, the vectors, the new vector corresponding to the last word, Y4. You can just take it to calculate what is go back to your vocabulary set to see which word has the highest probability to be the next one. It's because through the attention mechanism, we have already input the entire, to a certain degree, the information of the rest of the sentence to it. So that's turns out to be the basic idea of the transformer architecture. Now, it may not be how we human, most likely it's not how we human process, languages. But this is the basic idea of the transformer models, and is working pretty well. Now, of course, in reality, things are way more complicated than what I just told you. For example, there are a lot of linear transformation. Again, linear transformations in the actual models. Surprisingly, the things that you learn in linear algebra are super, super important. These linear transformations will act on basically most of the vectors. I should say almost all the vectors. You multiply a certain matrix to it to create this linear transformation. And these matrices are essentially where parameters enter into your model. Remember earlier we talked about these large language models. They have billions of parameters. This is where these parameters coming in. And in all machine learning models, as I mentioned earlier, looks like at least in the context of language model, the more parameters you can pack into your model, it looks like it gives it the better ability to understand, languages. And so this is where the parameters enter into the picture. But the main point is, hey, it's linear transformation from linear algebra. And now, I just mentioned just one transformer block. In reality, usually we will have the same input will be processed by multiple transformer blocks. Each time the parameters will be different, because each time we hope that different perimeters will help us to project into a different space, different subspace into the vector space containing the sentence. So we can sort of like each block will allow us to explore different aspects of the same input. So to, you know, understand the richer pattern of a single input. So to help the model to have better ability to understand, or at least to pretend to understand the input. So in general, the same input will go through multiple times these transformer blocks. Now, if you want to go into more detail to see how all these perimeters are actually working, I recommend at least two resources. Linian Wang, she is a team leader in OpenAI. Right now, she is a team leader in a Safe AI group, and she wrote a very interesting mathematical oriented blog. And also Kevin Murphy, he is also a team leader in Google Research, and I think he is doing, you know, computer vision. His books are great. Also, they're all available online. Probabilistic machine learning. This is one of the books that I use in my advanced statistics course in data science. Now, hopefully, I can also provide some nooks to fill in some of the gaps that I leave out in this talk, and I'll try to get it done, you know, by the end of this semester, hopefully. Now, AI really presents a great opportunity, not just for folks in computer science, but also for our math majors, for you, for many of you. And I want to, you know, highlight some of the work that, you know, our math majors are doing with AI. Helena is a math and English double major. And yes, you heard it right. It's math and English. She's a double major. And since last summer, she has been working on a project evaluating ChatGPT's capabilities in poetry generations. Because, you know, poetry is something close to her, dear to her heart, because she herself is a poet. And not too long ago, she published some math-inspired poetry in a math education journals. We are working on a little on a story about this, and hopefully we will able to post it, you know, post this online in our department website soon. Also, Sam Loomis. Sam Loomis is also a math major. He is building, actually, he is building a physical, he is building an AI chatbot. And he is not using cloud service to build it. He actually acquired quite a lot of computing units equivalent to 2 GPU, and he is running it at home. And he is training an AI chatbot to in particular to be a subject matter expert in STEM disciplines. He is training his model with 15 terabytes of data, a lot of data from archive, scrapping all these information from archive, and using servo language models, and he's running that at home. This is amazing. Now I gotta have apologies to Rudy, Chris, and Nish. Oh, talking about which, let me backtrack a little bit first. Thank you, Chris. See, earlier I talked about neural networks. We have an in-house expert in neural networks, Dr. Lian Kong, you know, department. He is doing some very interesting math modeling involving neural networks. Also with Chris Ding, they're exploring some interesting problem in physics-informed neural networks. We should have them talk sometime later. But one thing I know that, you know, my apology to Rudy and Chris and Anish is because I know Rudy and Chris, they are scheduled to talk about their work sometime this year. and he is a math minor. The AI campus learning community is also scheduling to have some to feature some of his work. So we will let you know when these happen. Oh, talking about the UIS AI campus learning community. This is a organization I co-found with Dr. Neetu Singh from MIS, and we are promoting all things AI for our campus community. And just before I stop, I want to have a short announcement of what is happening this year and next year. This coming spring, this semester, we are going to organize, host several special events. The first one is on February 21st. Is we are partnership. We are partnering with Hei-Chi Speaker Series, bringing a speaker to talk about AI, data literacy, and society. And on the March 7th, we are going to host a luncheon with a panel on unveiling AI bias through a multidisciplinary lens. And also late in mid-March, we will be working with UIS Music Department to have a panel discussion on performance psychology and AI. All these events have you can participate in person or via Zoom. And next year, the big thing is coming next year. We will be a partnership with Innovate Springfield to organize an AI conference here at UIS. Again, you can participate in person and also remotely. And more detail will be coming. Before I stop, this is something that you can do. For folks that are interested in, maybe there are some high school student, anyone who is interested in engineering, you see, some of the when I prepare this talk, I remember what I tell, people interested in science and engineering. Couple courses that you cannot miss: calculus, linear algebra. You see, linear algebra really play a really key role in the design of these language models, and also differential equations. What else can you do? Now, for math major, now some of you I know, some math major here, you already, expert programmers. But if coding is not your things, you can start learning coding through using generative AI, because all these, chatbot, they not only can talk to you. In fact, a lot of investment has been training these AI chatbot to do coding. Not only they can do coding, you can also learn coding using AI, these kind of AI chatbot. But by the way, I mentioned Google Bot earlier. Now maybe some of you haven't used any of these AI chatbot like ChatGPT or Google Bot. If you have a Google account, in fact, as long as you are a UIS student, you already have a Google account. You can go to you have Google Drive. That will give you just go to Google Drive, log in through your UIS username and password. They will have you to verify it through the 2FA authentic to use your 2FA to log in. And then you have access to a Google account. Once you get that, you log in, you sign in that account, you can use Google Bot, and you can immediately try out these amazing tools. Now, but of course, I got to warn you, if you apply to your other classes, you better check with your instructor what would be his or her AI policy in that class. Okay, for my class, I let them use AI. But for math major, AI, machine learning, this is just a great time to learn all this amazing math concept behind, and also learn some application of all these amazing tools. And if you're a high school teacher, you are interested to know, how AI could, help in your what you do. Contact us. We'd be happy to talk to you. And I guess that's all I have for this And that's all I have for this. Thank you for your attention.
All right, thank you very much for this very interesting and informative talk. Let's give our speaker thanks. And
Thank you for the talk. Can I get a quick recap on like the explanation of
Oh
like
yeah,
the
sure.
thing?
Yeah. Oh,
Thank
sure,
you.
sure. The transformer.
Yeah.
Yeah. The first thing is that there are two layers. The main thing is that there are actually more than two layers, but one, the self-attention is to help individual. Now, X1, X2, X3, X4 at the bottom, they are individual words. And they don't know, they have no, basically, they don't have any information about the context. So the self-attention layer is to help them to pick up some context information. In this particular architecture, they use linear algebra to bring in these so-called contexts. So what happened is that, for example, X2 representing the second word, it is being transformed to a new vector called H2. That H2 is simply the linear combination of all the other words. And so, does it make sense biologically? I don't think so. I don't know. But this is how it was being designed. And now, so that's the first major idea. The second major idea is that, okay, finally, you settle with the idea that maybe context can be encoded through linear algebra, but how do I choose the coefficients? So they come up with this assumption that, these coefficients would be proportional to E raised to the power of the dot product of the two vectors involved. They are trying to understand how the X3, the third word, affecting the second word. That's why there's a dot product of X2 and X3. This is not the only way you can do attention coefficients. There are a bunch of other ways, but this is the most famous one, and it's also in the one in the 2017 paper. So, so the idea is does attention layer help individual word to pick up some information about context of the input sentence. Then we pass it to a neural network. The neural network, in this case, is simply some nonlinear functions. Because, the experience with machine learning is that linear, if your model is purely depending on linear model, well, yeah, it is very powerful. It is very powerful. But when it comes to dealing with very abstract, complex patterns, like visions, like text, like languages, we better mix in some nonlinear function to mix up the signal. Think about these input as signals. It will give the model some complexity. And then it output the final output Y1, Y2, Y3, Y4. They are still vectors, but no longer the original X1, X2, X3, X4. They are supposedly like a black box, after we sort of push these original vectors through the black box. Now the output should contain some richer information about context. So in the very simple-minded, we will simply take the last vector Y4 and try to come and use it to further to compute, for example, what would be the most probable, next word, except for example. And but basically this block, this black box, this transformer block is the key of these LLMs, revolution since 2017. Now, as I say a couple of times, this may not be how we human process languages, but this architecture is underlying all the powerful AI chatbot that we are using, and is simply amazing. And this is why originally I came across transformer models before last year, but I didn't pay much attention. So first thing after I heard about, I learned about all this, AI revolution, just like every one of you with ChatGPT. I go to look at it, I think I'm amazed by, how linear algebra, how concept in linear transformation and linear algebra, how it play a very important role in all this model design, something that you already learned in linear algebra. So I hope this help. I hope this helped.
Okay.
Thank you. We'll
Thank
take
you.
more questions. So if you have any question, you can either mute and just ask, or you can type in the chat. I have a question. So just on this current slide, you have the parentheses, a small neural network. So just in comparison in the scale, and how small is that complexity compared to the
small because it has only one hidden layer. It has one layer less than this one. So the idea is, now usually when they use neural network, when they design a model to really use neural networks as the main engine, they will have many layers usually. But for this one, they only have a small neural network with one hidden layer. And so it is not really the main thing. It just, another way of thinking about it is they don't want their model to base only on linear transformations, because that may not capture these complexity of the data. So they just need some small non-linear functions to mix up the signal, so to pass it on to the next stage.
Okay, so they feed the information through linear transformation. That's basically the base of sort of telling you which direction they go, and then they add another layer of complexity through that neural network.
Exactly. Yeah. And they keep repeating this. They keep using this block. Just like many other neural network design or other sophisticated machine learning models. This is basically the how we model the modern machine learning model are designed. You finally figure out a way to process the input to an output. Then you do it multiple times, as many times as possible.
Okay,
That's the way of machine learning. But I could add one thing, is now maybe this is not how biological creatures work. Maybe you think about for bees, for ants, for tiny insects. They have small brain, but they are pretty smart. They may not have, if their brain really works like some sort of neural network, some kind of network, they may not have many layers, but they can still learn better. They are still pretty smart. And because this is another direction that, neural network design, neural network research are doing. There are people who talk about, small, tiny neural networks that can be made into a very portable model, portable modular units. Now, these sort of neural network, you cannot build you need huge facility to house it, to house all the GPU, and they have to take days to process things. But for the other direction is to research in tiny neural network that can be modular and portable.
So you mentioned that they run the information through several times of the block, and each time it will get closer to the goal, to what they want, right?
May
but at
not
some
be
point may not be. Okay, so how do they decide when to keep feeding it?
They test. This is empirical. They have to find it out empirically. They ran a lot of experiment changing. There's basically no. If you're looking for some kind of formula, there's no such formula. A lot of those design. They ran a lot of experiment, trial a lot of combinations to figure out one way to optimize, the performance of their model. In fact, how come there's been like 100,000 citations of that paper? It's because there's so many ways all these arrangements can have variation to improve the performance. So that's why there are so many papers try out different way to put things together to improve it. And so, everyone would come up with different sort of configuration to to make it work better. But that's a
Okay.
great question. That's a great question. There is no there's no formula pointing, oh, a 6 is the maximum. Don't go beyond 6.
Right, right.
Or 96,
Thank you. Very interesting.
See, in fact, in the early, in a couple years ago, when Google first came up with these transformer models, they have a more complicated design. They have basically 2 set of transformers. One set is what they call. They were thinking about doing translation. Now we know Google is very big on with Google Translation, so they actually those design. If you go back to that paper, 2017, Attention is All You Need paper. They have 2 sets of transformers. The first set is called encoder, and the second set is called decoder. Roughly speaking, that design is you input a sentence. The encoder consists of multiple transformer units. They will process that input into some sort of universal signal, some sort of very abstract signal representing the original input. Then the decoder will try to decode it into a different language. So in a sense, in that translation context, it is like you have an input, you first process it so that to make it to become a very abstract representation of that input, and then decode that abstract, input into through another language. Hey, Roxanne, I saw a hand.
Roxanne has a question. She posted on the chat.
Oh, okay. What is the question?
The connection between mathematical claims and truth isn't obvious, but let's grant that they are mathematical truth. They aren't contingent on the empirical world in the way that claims about good plans for a trip to Chicago are, or claims about mitochondria, etc. So I can see how ChatGPT might work pretty reliably for learning math. Can you say something about how the disconnection between ChatGPT and reality makes using it in other disciplines more problematic? Or do you think that claim is plausible?
Oh, that's a great question. That's a great question. I honestly, there's questions that I will not attempt to answer today because Roxanne, you're absolutely correct. There's a disconnect there. In fact, all these machine learning model, all these very sophisticated model, we don't have much clue why it works so well. That's why it comes to whether we can interpret why it will give the amazing result that these models are giving. We don't have any clue, and which back to something that we kind of earlier mentioned today. In fact, in business, Ryan, if I'm wrong, correct me. In business, as far as I know, a lot of business organizations, they prefer to use linear models, like regressions, like complicated version of regressions, because they're linear model. People can tend to sort of explain, to interpret those models, interpret those results. That's why, in that, in those areas, linear function-based model are more preferred because we can better interpret those results. But in contrast, these powerful, complex model that is doing this magical work, they are all full of mystery. Why, it will work the way it is. And you see, back to what Roxanne question. Actually, I don't think this kind of model capture the way we human work. It just happened that this is one possible way to make the machine work so well.
Yeah, if I make there's a famous analogy, which is, do submarines swim? And the answer is no, but who cares? So you know what I mean? So it's like, if the model is useful, then it's useful. And you're absolutely right that it used to be, particularly in fields like healthcare and finance, you needed to have model explainability. So you needed a linear model or a tree-based model that could be easily communicated to clients and stakeholders and regulators. But nowadays, because these deep learning models are so powerful, and you have a younger generation of kids coming out of schools that are familiar with them, such as the great kids at UIS, then these companies are hiring these kids and they're saying, okay, we're comfortable with these models because they're so powerful. Can you use the latest methods that have been developed to interrogate them? And because there's a whole other side field of interrogating these models to make them more explicable to management, the policymakers. And that's what I see going on around me right now.
Wow, wow.
It's
wow.
amazing how quickly all these things are moving.
I think, Ryan, you want to give this audience maybe give them some sense of your background. Your background is very relevant to what you just said.
Yeah, so that's actually why I'm studying math, is just so I can communicate with this younger generation of kids that are basically taking over our company and our department. They are coming in and they are using these tools. They've got adversarial networks at their disposal. They use reinforcement learning, deep reinforcement learning. They are setting up vector databases, which are databases where you not only encode words, but you encode environments, historical context, etc. And so I was sort of the person with one eye in the land of the blind, let's say, 8 years ago or 7 years ago or 5 years ago. But nowadays, I'm just trying to struggle to keep up with these younger kids, because the technology is changing so fast, and the value add is so much, that the older generation, their heads are just spinning. I mean, it's sort of like what went on with the development of software and spreadsheets and the personal computers back in the 1990s, but only going at a much faster pace.
Much faster pace. Yes, that's right. Much faster pace.
And that's why I've been speaking to Dr. Lee about this, because my daughter is 18 and she's about to go to university, and she's agreed that she wants to study computer science. And I'm really pushing on her to study mathematics, because the technology is changing so quickly, but the basics will not change. For loops, branching statements, calculus, linear algebra, these kind of things will not change. And so I'm trying to insulate her and prepare her for the future.
Right. Exactly.
Your math?
Actually, what's so wonderful is at the university here, there's actually a major which is applied math towards the field of machine learning. Wow, so that's the particular angle that I'm pushing. Yeah,
I think, Ryan, you're right, because I think trying to understand why things work is very important for her future, or the future of a younger generation. Because what we are seeing is that big companies, they are now investing a lot of money to use generative AI to do all the technical work. I'm also talking about writing codes, programming.
Yeah.
So
absolutely.
And now what would be the role of human? Human role will be, you have to understand how things work, so that you can be the one to judge the work of these, the work done by AI. They can do a lot of work much faster than a team of humans, but we have to understand why it works, how things work, so that we can able to judge the validity of all these AI generated work. And I think you're absolutely correct. In fact, this is also true when I talk to all of you, our math students, our math majors or math minors. Not just learn. If you don't know codes, now is a good time to learn some codes through generative AI. But at the same time, learning why it works, will also give you an edge as you go out to career in long run.
Right. By the way, the why it works is learning the math behind it.
Exactly.
Yeah, I think all these really quick change also brings in fears because people don't know what's going on. We don't know why it works so well. And then the fears of what is something wrong? What if AI just destroys humanity? That might be like the two extremes. So one is being really excited about the new development, just really want to go as fast as we could. And another is trying to hold back and see what's the fear of it. What could it do something really detrimental to us? There was just these two, the debates is pretty big as well.
That's why, in March 7th, we will have a event, which I mentioned on Safe AI, unveiling AI bias. It will be a in-person and Zoom event, and I hope that you all can join us, because it is very important to understand, how we can use AI safely, how we can use AI fairly and ethically, and so, that's why we have these events coming up. Very interesting.
Roxanne also raised the question that the right now the algorithms are pretty much opaque to even the experts. No.
Yeah,
I
exactly.
mean, it's true. But you know what's so wonderful, Roxanne? I'll give you one example. Is human beings have been searching for antibiotics for decades, and last year these models helped find 2 new antibiotics. So
Wow.
biological researchers found 2 antibiotics in just 1 year using some of these tools that they hadn't uncovered for decades. So that's the thing, is that it's true that to some extent we don't understand what they're doing, but that's offset by the manifest gains and benefits that we are just awestruck by.
Wow. Any other questions, folks?
Okay, this is very interesting. If you have any other questions, it is time to ask now. If not now, you can send me email or send Dr. Chen email. If you send me email, I'll forward it to Dr. Chen. And thank you all for coming. And it's a really fun talk for me, and hopefully you all have enjoyed it. I'll see you later.
Thank you.
Yeah, thank you for the time.
everyone.
Thank you.
Thank you.
Bye-bye, everyone.